Designing space-qualified optics means balancing tight, wavefront era budgets against brutal launch loads and thermal swings. Let's strip away the outer shell layer by layer to see how structural and optical engineering converge for high-precision performance. From the object side on the left to the focal plane on the right, here is how each component contributes to optimal optical performance. The first component is the main sunshade, also referred to as the front baffle. Its main job is to suppress stray light before it enters the optical path and causes signal noise. Because of its large surface area, we utilize low-density carbon fiber composites to optimize structural stiffness while minimizing total satellite payload weight. Next is the secondary mirror support structure, highlighted in orange. This structure holds the secondary optic in alignment and secures it directly to the main housing. Nested inside is the secondary mirror, shown in green. As a key optical element, its role is to receive light reflected from the primary mirror and redirect it along the optical axis toward the focal plane assembly. Connecting the primary and secondary mirror sub-assemblies is the main structural barrel. As the primary structural housing, it is engineered from lightweight composites to maintain precise optical spacing under launch loads and thermal variations. Positioned inside, highlighted in red, is the inner baffle. This secondary shield provides an extra layer of stray light attenuation, helping prevent off-axis light from reaching the detector. Here in yellow is the primary mirror, the main collector of incoming light. By utilizing silicon carbide with optimized rear pocketing, we achieve low CTE variation and high specific stiffness, helping maintain surface figure accuracy across extreme thermal gradients. Behind the primary mirror is the rear interface mount in blue. This precision mechanical structure interfaces the primary optical assembly directly with the sensor housing. Finally, we reach the camera module. Light reflected from the secondary mirror travels through the primary baffle and focuses onto the image sensor target. Every interface shown here, from stray light baffling to precision mechanical alignment, is engineered to withstand launch vibration and space qualification standards. And that completes the architectural breakdown of our space telescope assembly. Looking for custom space-qualified optical solutions or optomechanical assemblies? Talk with our optical engineering team today for your next mission.
Avantier, empowering optical innovations.